Here is the end of our derivation for the length of a line using integration. Now remember, there are a couple of things about this. So let me erase that little bit there. So a couple of things to note about this. This is what we use when we are given y as a function of x on an interval from A to B. And you can use either the notation that I have in black or the book's notation off to the right there. But either way, this is actually not so easy to use. There are only a couple of cases where this ends up giving you nice answers. So the book has a few of those problems in there, but almost always it gives you a really hard thing to integrate. And so you almost always use this formula to numerically approximate the answer, which is equivalent to just taking a really high n value in our MATLAB code. So a numerical approximation is basically the MATLAB code where we break the line into little mini segments and find the length of each segment and add those up. So when you can't actually find the antiderivative, you could just plug it into MATLAB in the code that we have, or just if you can write the integral, you'll be able to just put it into your calculator. So the reason this is so hard is we have a lot of steps here. Okay, so what I would recommend is break this down into steps. So in each of the steps, you're going to find and possibly simplify each of the following. So in step 1, we need to find what dy dx is. In step 2, we need to take the answer to 1 and square it. In step 3, we need to take the answer in 2 and add 1. Okay, now in the formula, it's reversed just because of the symmetry, because I had my delta x's first in the red box here, or the green box here. So we ended up with the 1 first, but we could just have easily have written the delta x and the delta y in reverse order and reverse that addition of 1. All right, so we have to do that. And then step 4, we need to take the square root of the answer to 3. All right, and then finally in step 5, we can say that the length is equal to the integral from A to B of the answer to 4 integrated with respect to x. So it's a little bit tedious to actually use the formula. Let's go through just a couple of examples, and let me start with one that actually works, okay? And it's an odd example. You'll wonder why it was picked, and it's picked solely because it works, all right? So the problem that we're gonna work with in example 1 is that y is equal to x to the 3/2 power, which by the way is the same as x square root of x, on the interval from 0, let's go out to 4. 4 has a nice square root, so that's a good interval to use. Okay, so let's do the steps. Step 1, I want to take the derivative of this. So dy dx is equal to 3/2 x to the 1/2, right? So that's the derivative in step 1. In step 2, we're going to square that. So we end up with 9/4 x. So squaring 3/2 gives me 9/4. Squaring x to the 1/2, or the square root of x, just gives me x. So step 3, I need to add 1. So let me write it out. Dy dx squared plus 1 is going to be 9/4 x plus 1. Now here's where, remember I said to look to simplify. One thing that we could do with this is to write it over a common denominator. So let me actually switch to blue here. So I could write this as 9x plus 4 over 4. Turns out in this case, that makes things better. all right? Because we're going to, in step 4, need to turn around and take the square root of this. The denominator has a nice square root. So in step 4, I can take the square root of, I'm just going to put everything in 3. So the square root of 9x plus 4 over 4. That also simplifies algebraically. The square root of 4 is 2, so I can rewrite this as the square root of 9x plus 4 over 2 before going on to step 5. So in step 5, I'm now ready to write out the integral. So I'm finally ready to calculate the length of the line by using the integral from x equals, remember we're going from 0 to 4, of everything that I have in step 4. So I'll write 1/2 in front, and then I have the square root of 9x plus 4 integrated with respect to x. Now, hopefully, you recognize this is going to be a pretty easy problem to finish. We know how to integrate this, right? It's not on the memory list, but you should go right to u substitution as a second guess. So if we let u equal 9x plus 4, du dx is just going to be 9. So du is equal to 9 dx. I would like to have an extra 9 with the dx, which means I better put an extra 1/9 in front. Let me put parentheses around that. Okay, so now we have the whole thing in terms of u. Oh, not yet. Let me do limits. When x is 0, then 9x plus 4 is 4. When x is 4, 9x plus 4 is going to be 40. Okay, so those are the new limits. Now we're ready to rewrite it. So the length will end up being, we have 1/2 times 1/9, so that's 1/18 out in front. The integral, now remember we're switching to u, so u goes from 4 to 40 of the square root of u, which we could write as u to the 1/2 du. All right, so now we just have to take the antiderivative of that with respect to u. So 1/18, whoops, not equals, 1/18, the antiderivative will be u to the 3/2. I'm sorry, we need to do, and then 2/3 of that. So 2/3 u to the 3/2. Evaluate it at u equals 4 and 40. Let's group the constants in the front together. And so we can say that L is equal to 1/27 when we group those. And then we have u to the 3/2, that's 40 to the 3/2, which we could write as 40 square root of 40. Minus 4 to the 3/2. Hopefully, if you do the same thing, you'd write 4 square root of 4, but hopefully you realize the square root of 4 is 2. So that would be 8 for that last term. So if we were to write it the way that the text is most likely to have it in the back. Now, believe it or not, this is as nice as it gets, or about as nice as it gets. The other examples are just going to get uglier. Okay, so let me actually break these examples up into a couple of videos. So I'll just call this part 1.